your obstacle center. And you also need information of the radius of the obstacles to determine whether the repulsive force is active or not. So these two obstacles, two circular obstacles, it's quite straightforward to use. And we also got one square obstacle. So you know for the square obstacle, or say for any obstacles that's not in the circular shape. The technique is to define an obstacle to cover, to define a circular to cover the obstacle. So in this case, you need to find the center, the geometric center of your square, and determine the radius itself. Okay, so I think the problem itself is quite straightforward to understand. So you need to develop some kind of force starting from the starting point, eventually go through all these obstacles, eventually go to the destination. So you know in the lecture we discussed the attractive force or the attractive potential by the destination, and we also discussed the repulsive force and the repulsive potential by the obstacles. But in practice, you only have these two potentials. The method is not stable. So if you do the simulation, you will find a problem. So to help you to get a physical path or physical results, so I'll give you some hint. Here you can define another force and another additional force. So this additional force is related, is inversely proportional to your velocity. So it's related to your velocity. So if you try set the KV to 0, then we will deactivate this force. So you can see what happens in your simulation. You will see you got a very significant oscillation. You cannot you cannot get to go to the destination, but instead it will oscillate in the space. So you know, we also discussed the known issues. So in some situation you need a small perturbation, especially when the attractive force and the repulsive force are balanced at a particular point. So you need a small perturbation to break the balance. So basically you require full forces at there. Full forces at there. So the requirements are also quite standard. So firstly, we need to derive the equation of the force, equation of the attractive force and the repulsive force. Because we already defined the potential, but you know the force is related to the derivative of the potential. So you need to calculate the derivative yourself to all the derivations. So next, you are required to formally formulate the problem. So you know we have this problem. So you need to develop a mathematical model. Mathematical model is just a different equation. So last time we discussed the x dot equal to vx, and y dot equal to vy, and the vx dot equal to ax. So in this case, ax, you should use the equation of the forces. So also for the Ay, you need to put the equation of the forces into the equation. So the first requirement is ask you to show me what equations, what set of different equations are you going to solve this problem. So the problem needs to be well defined. So next, the requirements is also the same, or are very similar to the requirements for the ESD4 assignments. So you need to describe how you solve the problem step by step. So this is very, very important. So just help you to write a potential professional report. So you know in the future you will submit the FIP report, which are 30%, 30 credits. It's very important. So the basic criteria to mark your report is whether it's clear or not. So here, ask you to try to practice, try to describe your method step by step to show me how you approach the problem, how you solve the problem. So you can include the flow chart and some key MATLAB codes. But if you use any MATLAB codes, remember we require the detailed explanations. So why you set the parameters and what are you going to do with the MATLAB code to make sure others can understand your report, understand your method. So you know we have some parameters at here. So for each force we have a parameter. We have a Ka, we have a Kr for the repulsive force, and we have a Kv for the additional force. So these parameters, these design parameters, are very important for the behavior of your vehicle. So in the slides from Glasgow, you can see some results like this. So these results I just extract from the slides from Glasgow. So when you choose different set of parameters, you will see very different behavior of your vehicle. So for example, for this set of parameters, you can see the vehicle will somewhat bounce at here at the obstacle. At obstacle, for some reasons, maybe because the repulsion force is too significant, so it's bounced back. It's something you can get a behavior like this. So when you change the parameters, you can get another path like this. So this path will exactly follow the obstacle. And if you change the parameters, you may have another set of behavior. For example, the vehicle will slightly go into the obstacle. So all this behavior will be changed and determined by your parameters using the same equation. So the third requirement is ask you to change your parameters to think about, we have three parameters at here, to think about how to choose the parameters. You know, you cannot choose the arbitrary parameters at here. So the parameters must follow some rule. You think about the force, think about the potential, think about what happens in the real scenario. So set the parameters wisely. So you should have some reasons to choose a particular parameter. So the absolute value of the parameters are not so important, but however the relationship between the parameters is more important. So for the parameters, set parameters, at least you should show these two sets of behavior. You may have another behavior. For example, the vehicle will go into the obstacle. So that will be better. But at least you should show these two kinds of behavior in your path. For example, when your vehicle is close to the obstacle, for this one, you will see the vehicle bounce back. And here, some kind of oscillation, and go to the next obstacle. To think about how to choose the parameters, how to check the behavior of the vehicle. So you are required to show your simulation path. And And more importantly, you are required to explain, to discuss, and comment your selection of the parameters as well as your results. So we introduced the first requirement is related to the additional force. We introduced this additional force in relation to the velocity. But this force is not defined in our lecture. And then this requirement asks you to discuss what's the effect, what's the reason why we need this additional force. So I put a hint here to help you to think about it. So you can also take the parameter of AV to see what happens. So you also need to put your code, your MATLAB code with a simple explanations in the appendix. So I put a note here from reviewing the ESC4 report. So if your report only contains a MATLAB code, and you just simply put the results without any explanation or any discussions, so I cannot be convinced that you do the experiment by yourself. I will think you just copy the code and just take the parameters, get a simple result, and put in the report. So I'm not convinced that you are doing the assignment by yourself. So in this case, you will get a 0 mark for this assignment. So this assignment will be available shortly. So in the afternoon, you can download this assignment. So I will give you 3 weeks to work on this assignment. So now is week 2. So this assignment will be due on week 5, on the Friday of week 5. So this assignment itself, the formulation is quite straightforward. We already discussed how to build up the different equations. So a key challenge is to use MATLAB to solve the different equations, because the differential equation is quite complicated to solve in mathematics. So it's far beyond what's covered in this course, and far beyond the background. So we are using MATLAB to solve the differential equation using the numerical methods. So from the slides from classical, there are some information. To tell you how to solve the differential equation, or say the ODE, the ordinary differential equation, by using MATLAB. So the basic engine by using this function, this MATLAB function, is ODE 45. So this ODE 45 is the main engine to solve the differential equation in MATLAB. So essentially, you require two functions. So the first one is the main function, the main MATLAB function. In the main MATLAB function, you can define the obstacles. You can define the set of the obstacles. You can define the radius of the obstacles. Define your start point, your destination, and all the parameters like the KA, the KR, PV. And you also use this ODE 45 to solve the differential equation. So after that, you can plot the results, and plot the results here. So this will be the main MATLAB function. But now the question is how to enter the differential equation. So you know here that the code is quite standard. But we are using this engine to solve different differential equations. So how to let MATLAB know what different equations you are going to solve. So in this case, we need to define another function. So you can notice there is an add here, a special capital here. So this add means this parameter to this function is a function handle. So I'm not sure whether you have the concept of the handle of the pointer from your software engineering or previous programming course. So you know for any variable stored in the memory, you got a particular address in terms of the computer memory. So the pointer is actually contain the address information. So the concept, the basic concept like this. So for example, you define a variable a equal to 10. So you know this 10 will be stored somewhere in your memory. So for example, you got a memory at here. That particular memory, you got this value of 10 at here. So this is the value of your variable. But you have another information, important information in the address. Is the address of your variable. So this address is the pointer. So in this case, it's a pointer for a particular variable. So you can think about that your code, your function is actually also stored in memory. So in the memory got a particular space for your function. So here is your function, the MATLAB function. So in this case, you also need a pointer to tell you the address of your function. So in this case, it's the handle. It's the handle that we define here. So I just give you the basic concept. To remember that this function you need to declare your differential equation to be a handle. So you just define in this ODE40 file. If you help this ODE40 file, if you do the help this ODE40 file, then it will feel MATLAB will show all the related help information for this command. So you can understand the other parameters as here. So basically, this can define your initial condition, the initial condition of your final condition in order to solve the differential equation. And you can also input the parameters like defined here into your differential equation. So it's just a way to find in MATLAB how to transform the parameters into another function. So this is the main script. So we need another script to define your differential equation. So in this case, we declare this function to be MSD ODE. So in this case, we define this function. But you may use any name at here. So it's up to you to choose this name. So this function is to define the differential equation. So an important parameter is at here. So we have this state. So you can understand this state to be something like defined in the state space method. So you know in the control you use the state space modeling technique. So you are quite familiar with the state. So we are using the same concept as here. So this one is the state. This one defines actually the derivative of state. So it's the state dot. the derivative of the state. So remember that our derivative is taken in terms of time. So that's why you must have a variable time right here. So although we are not using this time, but if in your declaration of your function you don't have this time variable, you will get an error. Remember, you require this time variable. So this will be the parameters that transferred from here. So you define your parameters in the main program. So you want to transfer the parameter into your differential equation. So the way is to define the parameter here. When you transfer, you use these parameters in this command, in the ODE45 command, and then this parameter will be transferred into your differential equation. So this is the interface for the differential equation. So now how to define this differential equation? It's also quite straightforward. So this code, this several line of code is to address this problem. It's just a simple 1D problem. So I can put the equation in a form that you are familiar with. So for the 2D problem, for the 2D differential equation, or for the 2D potential function method, we define x dot equal to Vx and y dot equal to Vy, and Vx dot equal to the Ax. So this is equal to summation of the force in the x direction. So we have the fxa plus fxr plus fx noise plus fx additional, and you may define other forces. So similarly, we have the Vy dot equal to Ay. So this linked to Fy. So we just define this f equal to 1 to normalize the mass to 1. So this for the 2D problem. And this code at here is just to show you to solve a 1D problem. To show you to solve 1D problem. So what happens in a 1D problem? In a 1-dimensional problem, we only got this x. The x is the location. To think about it, you got your vehicle, we have a 0, or your starting point at here, and we have a destination at here, and you only got x is defined in this direction. So the problem can be simplified to be x dot equal to Vx, and this Vx dot equal to some forces. So in this particular example, is defined this Vx dot equal to minus Ax minus Vx. So it just defined in this example. So I will not further discuss why we define the Vx in this way, but I just show you if we have a differential equation in this form, how to define the differential equation in the MATLAB. So now assume we have a differential equation like this. So in order to solve this differential equation in MATLAB, we need to define the state vector. We define the state vector. Assume I see the state vector to be x vector representation here. So remember that this x is different from this x at here. So this one is a vector. I define a new vector, state vector. So this state vector I define to be the location and your velocity. So it's just a quite straightforward method as in your control theory. Remember this x is the location at here. So this is the location of your vehicle. So this is your velocity of your vehicle. So from definition of this x, we can define this x dot. So we can define this x dot. So this x dot, this will be this location, this small x dot, and this Vx dot. So in this case, we know the x dot from the differentiation is equal to Vx, equal to Vx. And this Vx dot, I define this to be minus Kx minus C Vx. So now we define the state. So these are the state, the x. And we also define this state dot, this state dot. So we can put the information into the equation. So we already defined this state and the state dot. So in MATLAB code, so I define this state 1 to be x. So the state, this state 1 to be x, the state 2 to be Vx. So in your function, in the MATLAB function, in the MATLAB function, you know the input variable is this state. The state is a vector. So the state 1 we define to be the x to the location. So I just define a new variable, this x equal to state 1. And similarly, we have this state 2. So state 2 is a Vx. So we define this state 2 to be Vx. So the the goal, or say the objective, is to define the state dot. The state dot. So for example, I define the state dot to be dx dt. So it just a name. It's not a name. It's just a name defined in MATLAB. So the dx dt. And we have this dx dt. 1. The dx dt 1, or say the state dot 1, the state dot 1 equal to x dot equal to Vx. So that's why I have the Vx and here. So similarly, we can define the state dot 2. So this is the dx dt 2. So the state dot 2 equal to Vx dot 2 equal to minus Kx minus A Vx. So this equal to minus k is a constant, multiplied by the x defined at here, minus c is a constant, multiplied by Vx at here. So now we already have this state dot. So you know when we define a function here, so in a function you need to retain your output to the main function. So you will retain this state dot. But remember that we declare the state to be a column vector. So in this case, we define the state vector to be 2 by 1. So you got two rows. It's only one column. So the state dot should also be a column vector. So it must be 2 by 1 as well. But if you define it this way, so in MATLAB, this dxct will be a row vector. A row vector. So that's why we require this final command. This final command to guarantee your output is a column vector. So remember, this is also important. So eventually, this dxpt will be a column vector. Column vector. Okay, so this is the key idea how to use MATLAB to solve this 1D differential equation. So for this 2D problem, so you can think about that you require 4 components and here. So in your state vector, you require 4 components. Define your x, y, vx, and vy. Then your state dot will also contain 4 components. So when you define the state dot, you need to retain this 4 component column vector to the main function. So eventually, when you solve this problem, this time will be your, we solve this problem in terms of a particular time. For example, it's starting from time of 0, and then like here, we solve the problem from time equal to 0 to time equal to 10. Then you will got a variable. So this time will be a vector from 0 eventually to 10 with multiple components. Multiple components will be vector. So this x out will be your final output. Your final output will be the form that here. So this x out will be. So in this case, we only got 2 components. We got the x, we got the vx. So in this case, the first column. So you know this x out will be a matrix. So this one is a matrix. And the first column will be your x. So the second column will be your vx. So you can think about this one, for example, to be n multiplied by 2. So this n will got the same length as your time. So your time will be n by 1. So we got the same length. So that if you plot your output in this way, you will plot your x in terms of time. So this command will plot your velocity in terms of time. So all of this depends on how you declare your state vector. So if you declare your state vector to be x, y, vx, and vy, then your x out will get 4 columns for the x, y, vx, and vy. Okay, so I think you should clear how to use the ODE40 file to solve the function. Okay, so it's important for you to try it by yourself.
现在这个钉子钉没的。
So in the last lecture, we discussed the optimization, the unconstrained optimization problem. So we have discussed how to define a cost function, I'll say what are the ideal property of a cost function. But our purpose is to solve the optimization problem, to find the minimizing solutions. So our aim is to find the optimal control in the function to solve the problem. But now we don't want to solve a particular optimizing problem. So it's important to find the property of the optimal control. So the first property is related to the location of the solutions. So for example, if we have this 1D problem, so we know there are some minimizing solution and some maximizing solution. So for example, this one is a maximizing point, this one is a minimizing point, this one is another maximizing point, this one is another minimizing point. So in mathematics, we can know that in order to find the minimizing solution, so you know in this case, this one is a minimizing solution, this one is another minimizing solution. But in general case, we don't know this function. So we want to find the property of this particular point. So what are the general property of this minimizing point for any functions, any n-dimensional functions? So the first observation is that the minimizing point must be extremal. So in mathematics, we know the extremal is defined by the derivative, the first derivative equal to 0. So if you evaluate the derivative of these points, you know this one will be equal to 0, and the points in between are not zero. So from this observation, we know for this 1D problem, to determine your minimizing solution. So firstly, you need to calculate the first derivative and determine the location of the points that make the first derivative equal to 0. So this will be our necessary condition, because in this simple example, we know the minimizing point must be one of the location of the extremos. But however, not all the extremos are the minimizing point, because for example in this case, it's a maximizing point. But in this point, the derivative is also equal to 0. So we have this necessary condition. So the necessary condition for the minimizing solution is we calculate the cost function. We calculate the derivative of the cost function in terms of your control input, and at the minimizing point, this derivative should be equal to 0. So we can see a simple example. So for example, we have the cost function to be u minus 4x squared. So it's just a one-dimensional problem. So you know for this one-dimensional problem, we can graphically show, we can illustrate the figure of the function. So this function is a very simple function. You know, for u equal to 4, for u equal to 4, this one will be equal to 0. For any other value, this one will be greater than 0. So u equal to 4, we have this j equal to 0. So for any other u, this j will be greater than 0. You know you already learned this simple function in your high school. So for example, we have this u, we plot this j. So the 4 is a 0. You know it's a parabolic form, something like this. So this function only got one extremos. Only got one extremos. So if we plot this form, we know the extremos is u equal to 4. But before we do this, how can we determine the location of the extremo? So the standard mathematical method is to calculate the derivative in terms of looking to equal. So we can calculate this dj du. So in this case, we know it's d is u minus 4 squared du. So we know this are equal to, so this equal to 2u minus 4. So the necessary condition is to set this equal to 0. That will give you the u star. So we set this dj du equal to 0. This will give you this u star equal to 4. We only got one solution at here. So this can be verified by our figure. In our figure, we know the u equal to 4 is really a minimizing point. But this condition is just a necessary condition. So what happens for the point that satisfies the first derivative equal to 0? So we know there are three situations. So the point could be a minimizing point, or could be a maximizing point. Another case is this inflection, the point of inflection. So it's a changing from the changing of the form, changing of the shape like this. So in all these three situations, if you calculate the dj du and evaluate at this point, evaluate at, for example, this point is u1, this point is u2, this point is u3. So if you calculate this derivative and evaluate in u1, this will be equal to 0. Evaluate u2, it's also equal to 0. Evaluate u3, it's also equal to 0. Because our aim is to find this kind of points. Think about if we got a cost function. So this, for example, this cost function describing the traveling time from the starting point to the destination. So you want to minimize the traveling time. So you want to find the minimizing solutions to this function. So we are very interested in this situation. So how to distinguish these three situations? So in mathematics, if we evaluate the second derivative, that will be distinguished. So in all these situations, this dj du at this u1, u2, u3 are equal to 0. But however, if we calculate the second derivative, we will find in this situation we have this d squared j du squared for u1 is greater than 0. So in this case, for u2 is smaller than 0. And in this case, for u3 is equal to 0. So in this way, we can distinguish. So our first step, the necessary condition is to determine this location, these potential locations for our solution. but these potential solutions are not unique. So the second step, the first step is to determine the potential locations. So the second step is to determine whether the location is a minimizing solution. So whether the location is a minimizing point. Is a minimizing point. So these are the idea to approach the problem. So the idea can be further illustrated in a simple example. So you know for the cost function, if we define this cost function to be j equal to u minus 4 squared. If we define the function in this way, the function will have a shape like this. So we have a minimizing point. So this point is the minimizing point. So to verify this point is really a minimizing point, we can calculate the second derivative. So from our previous step, we already determined if we calculate this dj du, the first derivative equal to 0, you get the potential location to be u equal to 4. We only got one potential location. So the next step is to evaluate whether this potential location is a minimizing point. So the method is to compute this dj squared u squared. So the dj du already give us is 2u minus 4. So we know this dj du equal to 2u minus 4, so this equal to 2u minus 8. So if we further calculate this 2u minus 8 du, we know this one is just a constant. This will be equal to 0, and this will give us a 2. So this 2 is just a constant for any u. That means for any u, we have this second derivative equal to 2. You know this equal to dj squared du squared. We have this one equal to 2 for any u, for any control input, including our u equal to 4. So that we can verify that this point is really a minimizing point because it satisfies both conditions. So similarly, we may have another example. So if we define this function like this, so now this point become a maximizing point. So how can we verify this? So we just do the same derivation. We will find that now the second derivative is equal to minus 2. So it's smaller than 0. So it's du is minus 2u plus 8. We know this one is equal to 0. So this is equal to 2. This for any control input, for any u, and certainly including this u equal to minus 4. Okay, so it's quite straightforward to understand. So now we have our solution to the unconstrained problem. For the unconstrained optimization problem, the method to solve the problem is to evaluate the necessary condition and the sufficient condition. So the necessary condition is to evaluate your cost function in terms of u, and set is equal to 0. You evaluate this dj du, and you set this equal to 0. So hopefully this will give you a set of solutions. It's u1, u2, u3, something like this. Something like this. So the necessary condition is to determine these potential locations. So next, we need to evaluate the sufficient condition. So the sufficient condition is to evaluate the second derivative, but only for this particular point. So we evaluate this dj square du square for this particular point. It's u1 to see whether it's positive or negative. And for u2 is positive negative. So for example, if eventually if this one make the results to be smaller than 0, this one makes the results to be greater than 0. So we know this u2 will be a minimizing solution within this set of potential locations. This is a minimizing solution. So to solve the unconstrained optimization problem, both of the conditions must be satisfied. So far we have discussed the 1D problem. So the 1D problem is quite straightforward to understand. But however, you know our inputs are not just a single input. Generally, we have multiple inputs. So in this case, we can expand the conditions to the n-dimensional space. So what happens when the controls are multiple controls, uncontrolled here? So this part are very important. So in this case, we define the control input to be, I also use this way. So the R means it's a real space. It's a real space. And this N is the dimension. It's a dimension. So we define this U to be a column vector. So we define this U to be something like this. This to be U1, U2 up to UN. So you have this N control input. So you can use this N input to control your vehicle. So the necessary condition and the sufficient condition have the same. These two conditions have the same formula, exactly the same formula, but it will be more complicated. So in this case, is to evaluate the derivative of the cost function in terms of your control input and set this to 0. So if your function only got one input, as something here, you know how to calculate the derivative. But what happens if your function got multiple input? I have n input here, like this. So for the first derivative, so this dj du, we can define this function like this. So you know this j is a scalar. It's a scalar cost function. So if this one is also vector, that will be more complicated. But fortunately, we define this J to be a scalar function. So the J is a scalar function and we have multiple input and here. So this one is n by 1. So for the n by 1 vector, so to calculate a scalar function in terms of n by 1 vector, you will also got n by 1 vector. So the first one will be the dj in terms of your first component in your vector. So this du1. The next one is a dj du2, something like this, so up to dj dun. So you know this also be a n by 1 vector. So to evaluate the necessary condition is to set this equal to 0. Set this equal to 0, so you solve all this, you solve this n equation. Solve this n equations. So this will give you a set of potential locations. For example, the first one, this U1. But remember that this U1 is different from this U1. This U1 is a vector. The vector of U1 contains this n points, this n coordinates. So think about it in a two-dimensional space. Your first location will be include x and y. So for example, in the two-dimensional space, this one will include x and y, x1, y1. And you may have another potential location, it's U2. This could be x2, y2, another point in the space. So this may determine a set of, for example, up to m potential solutions, m potential minimizing solutions from the necessary condition. So next, we can evaluate this sufficient condition to determine which one of the points is really a minimizing solution. So the form is quite similar to our one-dimensional case. So it's to evaluate this two-dimensional, this second derivative. But now it's more complicated. So you know this one, this dj square, du square, this one is equal to d du but here is a dj du. So we define the second derivative this way. But now you know this dj du already become a vector. So now you are evaluating vector, the derivative of a vector in terms of another vector. So in this case, you will got a matrix, n by n matrix. So this one will be n by n matrix. So now the question is how to evaluate this n by n matrix to be positive. So definitely it's not to evaluate all the components to be 0, to be greater than 0. You know, if all these are positive, it doesn't mean your matrix is greater than 0. So for the matrix to be greater than 0, so it's defined in another way. You know, for a matrix to be greater than 0, it's defined to be positive definite. I think you already learned this before. So you know, for the general definition, if we see a matrix, for a symmetric matrix, we only define the matrix to be positive definite or not if the matrix is a symmetrical matrix. So if a symmetrical matrix A satisfies another condition like this to be greater than 0 for any vectors, we may see this matrix is positive definite. So here I want to see the matrix to be why the matrix is symmetrical. So for the second derivative, for this Hessian matrix, if we observe the structure of the matrix, we can see that for this dj squared du1 du2, so we have another component here. This du2 du1, so up to this one du1 dun, and here we have a du1 du1. So that means these components are the same. So for a matrix, so for example, if we see a matrix H, so if the matrix is symmetric, that means this H equal to H transpose. So for the transpose, I think you should be quite familiar. It's quite simple. It's just like this. For example, if we have a matrix 1, 2, 3, 4, we have a matrix like this. If we calculate the transpose, we got this 1, 2, 3, 4. We just change the order of the components. So for the symmetric matrix, we can determine whether the matrix is positive or not, whether it's greater than 0 or smaller than 0. So we will further discuss this in the next lecture. Okay, so we just stop here today.